So welcome everyone to the Toronto Set Theory Seminar. Today's speaker is Mohammad Golshani, and he will speak about ultraproducts and the continuum hypothesis.
Okay, thank you for the invitation and thank you for coming. The talk is based on some June works with Sheila. One of them is available on archive and one is in progress. So, and it's about the relation between ultraproducts and the continuum hypothesis. Yeah, I would like just to establish the convention that in this talk, all languages are assumed to be countable. And I start this by a definition, which is motivated by a theorem of Kessler that I will state it later. Suppose kappa is an infinite cardinal. I define KT of kappa. Say Kessler theorem for cardinal kappa. It says suppose M and N are models size at most kappa, which are in the same language, I mean, which are elementary equivalent. Then there exists some ultrafilter D on omega such that the ultrapowers are indeed isomorphic. Of course, I can also define weak Kessler theorems at kappa. And it is the same, just we assume that the ultrafilter D is an ultrafilter 2 to them. The same definition, just ultrafilter is taken on 2 to the omega. Now let me state just some noun results. The first one is Kessler's theorem from 1961, which says that the continuum hypothesis implies KT of 2 to the aleph 0. So under CH, if M and N are two models of size okay, at most aleph 1, then they have isomorphic ultrapowers. And 10 years later, shall I show that we can remove CH from Kessler's theorem, but instead we get just the weak version of the theorem. So we have KT of aleph 0. Oh, sorry, weak. And also in 90s, maybe in 1991 or something like this, shall I prove the consistency of the failure of KT aleph 0? So this shows that Kessler's theorem is not a ZFC result. And to prove this, shall I build a model in which 2 to the aleph 0 is aleph 2, and in which there are two countable graphs such that they have no isomorphic ultrapowers for ultrapowers on omega. And now I would like to state some results which are obtained by Scheller. The first one that I would like to state is just a ZFC result, and it says that KT at Aleph 2 fails. And this has the following trivial corollary, that KT 2 to the Aleph 0 implies CH. So in the case, the theorem is equivalent to the continuum hypothesis. And now I would like to sketch just the proof of this theorem. The proof is quite simple. Okay. So in order to show that KT of Aleph 2 fails, I have to build two models of size at most Aleph 2, which are elementary equivalent, but they don't have any isomorphic powers. And the theory I take is just the theory of dense linear order without endpoints. So L is just the S relation, and the theory is just the theory of dense linear orders without endpoints. And for the models, I take M just Q with the less than relation. This is the rationals. So it is countable. But for N, I take just a model of T of size Aleph 2 such that N has 2 points, A and B, such that the cofinality of NA is Aleph 1 and the cofinality of NB is Aleph 2. And what is NA or NB? In general, if this is my order A, and if I have some point C here, by NC, I just mean the initial segment generated by C. So NC is just a set of all points in N, such that D is less N of C. So we require that the model N has 2 points A and B, such that NA has cofinality Aleph 1 and NB has cofinality. And I show that, oh, okay, it's clearly M and N are elementary equivalent because the theory of dense linear orders is complete. Okay, now I show that they don't have any isomorphic ultrapowers. So suppose towards contradiction, there exists an ultrafilter, say D on omega, such that N to the omega or D to the omega T. They are isomorphic, and let's say F be an isomorphism from this is just the correct. Now, actually, which just maybe I just should N here. But that, as I said, N has 2 points A and B with some special properties. So here I just transfer information. So I get a point that I denote it by A star, and it is just the equivalence class of the fixed point sequence A. And similarly, I can get the B star. It is quite easy to show that the cofinite. Okay, just for simplicity, let's denote this model by N star and this model by M star, just to simplify the notation. Now it is quite easy to show that the cofinality of initial segment of N star by A star is Aleph1, and cofinality of N star by point B star is Aleph2. And here the point is that ultra filter is on omega. This is very important in the proof, but it's quite easy. So what happens if we have some F here? So I can consider F of A star and F of B star. And since F is an isomorphism, so I can conclude that, say, let's call it A plus and B plus. So I can conclude that cofinality of initial segment of M star by A plus is Aleph1, and cofinality of M star by B plus is Aleph2. But look, M is just Q. And we know Q is homogeneous. Indeed, any point in Q has cofinality omega. And we can say more, because just having cofinality doesn't mean to be able to transfer it. But indeed, we have something more, and it's, again, quite trivial. There exists some F of X, Y, Z, such that for all B and C in Q, F of X, B, and C is an automorphism of Q sending B into C. So F, X, B, C is a function of X, and it sends B into C. And this is quite clear, because just here we want is just sufficient to take F of X, Y, Z to be X minus Y plus Z. So we have a definable way to show that any 2 points in Q have the same cofinality, and now we can transfer this, because this function F is defined so easily. Cofinality of M star of, say, any point in it, in particular A plus, is cofinality of M star at B plus. And this is a contradiction. Okay. Do you have any questions? Do you hear me? Yes?
Yes.
Okay. So it shows that if we want to prove consistency results in the absence of CH, we just can talk about KT at Aleph0 or KT at Aleph1. And the next theorem that I would like to state that I won't prove, because I want to prove something more new, is the following. Suppose 2 to the Aleph0 is bigger than Aleph1, and this is just the cofinality of the continuum. And suppose covering of the meager ideal is just 2 to the left 0. And the covering of the meager ideal is just the minimal size of a family of meager sets which are needed to cover the real. Then KT, at left 1 holds. So in particular, it's consistent that the continuum is arbitrarily large and KT at LM1 holds as okay. No, I don't prove this story. It's not difficult to prove it, but I would rather to talk about more recent results, which are not yet published. They are in preparation, and they are in some sense an extension of this story. Now I would like to discuss about not just taking 2 models, M and N, instead taking sequences of models. And for this, I make a definition. In this definition, I talk just about countable models, but indeed we can allow the models to be of size Aleph1 as well. But just to make definitions easier, I just talk about countable models. I want to define the notion of an ultrapolar problem. An ultrapolar problem indeed, this is a sequence. I denote it again. N1, N2, and tau n for n less than omega, where the first definition is that tau n less than omega is an increasing sequence of vocabularies, is an increasing sequence of finite indeed vocabularies. So it's that tau 0, just for simplicity, I take to be empty and set tau with the union of tau. So tau is a countable vocabulary. And each N1 and N2 are in the models of tau. Or tau models. And just, you will see why I take these tau n's. It will become the next part. And this is the third part of, at the end, I want to prove a theorem which says that the ultraproduct of M and 1s, if they are elementary equivalent to the ultraproduct, on the product of M and 2s, then they are isomorphic. So I need a kind of some local isomorphism because it's needed. And this is the third lim sup of the sequence Kn when n goes to infinity is infinity, where Kn is defined as false. And I want to define Kn using an Reference Pn. So Kn is the maximal K less or equal to N, such that player 2 has a winning strategy in the following game. And it's a kind of Ehrenfeld process. I denote it by G, N, K. The game that I now define is not quite precise, but I just want to highlight the main idea. Indeed, I'm giving a more strong kind of game, but we can weaken it a bit. So the game is something like this. Player 1 chooses two sets, A0 and B0. And such that the size of A0 plus B0 is just less or equal to K. And this is the K that I fixed. Then player 2 replies by a function, say F0, which is a partial isomorphism from Mn1 when restricted to tau n. And this is the role of tau s. So they are finite. So this is a finite, this is a partial finite isomorphism from this into Mn2 and such that A0 is a subset of domain of F0. And A1 is a subset of, B0 is a subset of range of F0. And then again the same, player 1 chooses A1, B1, such that they have size less or equal to K, and player 2 replies by some function F1 as before, but F1, just we recall, it also contains F0. So we have a game which at each step the player 2 tries to find an isomorphism, or at least local, maybe on just a finite set. So we require that the lim sup of this sequence to be infinite. And in some sense, this is needed for the theorem that I now would like to state. And the main theorem that I would like to state.
How does the K depend on the N? I'm very sorry.
Excuse me?
Can you go a little bit back up on your slide? Or so it's a sequence of K. OK is maximal less or equal to N. I see.
Yes,
okay,
yes.
Thank you.
K less or equal. And
so let me also ask, so is the tau n changes, so what happens, so the model restricted to tau n is the set with that those relations on it, is that correct?
Yes, yes.
So what happens when you go to a larger set, and maybe when you go from F0 to F1?
Okay.
I see. N is fixed here.
N is fixed, yes. N is fixed.
Oh, it doesn't depend on the FIs. Okay, all right.
Yes, yes. But you know, when I go to the next model, Mn plus 1, it increases. But now at the stage N, Kn just depends on N, and N is fixed. Okay. So the main theorem now.
This is still part of the assumptions on the sequence of the models, right? Sorry.
Excuse me. Sorry, I don't hear.
I'm a little lost.
Okay.
I'm a little lost. So this is still part of the assumptions on the sequence of models?
Yes.
Or?
This is part of the definition. This is part of definition of an ultra-power problem. The first two are just trivial things, and the third one is something that says we have some kind of partial isomorphism. But you know, it's quite weak because it just talks about finite sets. So what is the main theorem? And the main theorem is the consistency of 2 to the aleph 0 is large plus the following statement. Plus maybe I just write a star is, and a star is this statement. Suppose n is, okay, sorry, I just twisted the theorem. I need one more definition. So we have to make another definition. I want to assign to any ultrapolar problem a filter, which is indeed countably generated. Suppose n is an ultrapolar problem. Let dm, this is the filter related to m, with a filter generated by sets n less than omega such that kn is bigger than, say, or maybe k, or maybe just I, or I less than omega. So as I said, since the limb soup is infinite, each of these sets is infinite. And let dm be the filter generated by this countable elements. It's a non-principal filter. And now I can state the main theorem. It is consistent that 2 to the aleph 0 is large and a star holds. And what is a star? The star says, suppose m is an ultrapolar problem. Okay, I just recall maybe m, say it's mn1, mn2, and 10n. Suppose it's an ultrapolar problem, and suppose D is an ultrafilter. So is an ultrafilter on omega, which extends dm. So D could be quite arbitrary. It's not just one ultrafilter, it can be any ultrafilter extending dm. Suppose the ultraproducts of M and 1 mod D are elementary equivalent to the ultraproducts of M and 2 mod D. So if the ultraproducts are elementary equivalent, then indeed they are isomorphic. So as you see, in some sense, this is a very strong extension of both Killian's theorem and the previous theorem, in the sense that instead of taking just one ultrafilter, in some sense we are saying to say almost all ultrafilters, or almost all ultrafilters, ultraproducts are isomorphic, or provided that they are elementary equivalent.
Can you, before you go on, can you just show us again the definition of the ultrafilter dm, of the filter dm?
Yeah.
No, the definition of dm.
Oh, okay, here.
Okay, so it's
For
the
any
filter
I-
generated by.
For any I take all n's for which kn is bigger than I. And you know, this is
Okay.
infinite, yes, because lim sup of kn is infinite. So this is an infinite.
Yes. Okay.
And they are decreasing. Okay. So, and here is the theorem. And the proof of theorem is in two parts. Indeed, the proof has two parts. And maybe I just stated the first step of the proof is that to any ultra power problem M, I assign a cardinal invariant. And I will show that if it's Aleph1, then the conclusion of this theorem holds, and then we build a model in which the requirement on this cardinal invariants are satisfied. So first, the first step we assign to M a cardinal invariant. Maybe it's almost, it's DM, it is something like DM, and we show that it's somehow like band dominating number. And we show that if this number is Aleph1, then the conclusion of the theorem holds. And the second step is just to build a model in which DM is Aleph1 for all ultra power problems N. So the second step to build a model of ZFC in which for all M, which is an ultra power problem, dn is just, and in the part 2 is quite easy. Maybe if I define the invariant, we will see it. So what is dn? So fix n, then I define the n to be the minimal size of the family F, where F is in this ultra product of, in the product of M, or maybe I just can't talk about omega, because as I said, I assume all models are countable. I think I didn't write it. So when as I said before, I assume always are tau models and countable. But we can assume they are uncountable of size 11, but the definition becomes a bit more complicated. So I can assume the universe is omega, and this allows me to just talk about omega. So it's in the product of omega to the kn, such that for any function from omega into omega, there exists some f in this family such that eta n is in Fn for dm many points. So for all dm many points n, eta n is in F. And this just means that, sorry, I think. Do you see it well?
Yeah.
Okay. So this just means that the set of n's for which atom is in Fn is a member of the M. So this is the definition of the M. So it is a kind of dominating number. And now I would like to prove, I would like to prove part one, proof of one. So I would like to show that if dm is aleph 1, and if D is an ultrafilter, so maybe I just write it. So suppose dm is just aleph 1, and D includes dm is an ultrafilter, and suppose the ultraproducts of Mn1 mod D and Mn2 mod D are elementary equivalent. Yeah? So what we want to show that, these ultraproducts are indeed isomorphic. I build the isomorphism in omega-1 many steps using this cardinal invariant assumption. And for this, I first need to make this part of, maybe I just make it a definition. I say S is an approximation. It is going to be a kind of approximating the isomorphism, but not directly as it is. So I say S is an approximation if and only if S is a sequence Gn n less than omega, where the following assumptions hold. The first one is that, recall at step n, I had a gain, yes. In particular, if you recall, I had this gain. Gn is an initial segment of the gain. You know, I had this gain depending on n and k, and k was the maximal K for which this gain was possible, and player 2 had a winning strategy for it. So Gn is just an initial segment of this gain of length, say Ln. So Ln is at most Kn, yes. So it is at most Kn. And last function, recall that the gain was player one was choosing to set A0, B0, and then player 2 was choosing F0, and so on. So the last, if this function in this initial segment, let us show it by Fn. It is indeed FLN, but let's just simplify the notation and denote it by Fn. Okay.
Sorry, could I? I'm a bit confused though. I thought Kn was a bound on the size of the finite sets that you could have your I functions contain in the domain of the range.
N was the maximal K less or equal to N for which player 2 had a winning strategy in the game of length K.
So what was there was also a bound on the size of the sets that you could cover in the Fi. I thought that was Kn.
Excuse me, Oh, yes, they are the same. They are the same. This Kn is exactly the Kn which comes from M.
Right.
Yeah.
Oh, I see. So you're defining this to be the length.
What? Excuse me?
So, but you're saying now that the GN is an initial segment of the game.
Yes.
Oh, I
But,
see.
you know,
And the length. So now you're imposing a condition. That's not okay. I understand. All
Because
right.
now you're truncating the game. Now it's
Yeah.
sort of-
Size KN. Okay.
Yes, it's Kn. But the point is the second one. I don't want it to always be Kn. Indeed, I want the difference between Kn and Ln mod En is infinite. I want this also. And this allows me, for example, having some S, I can extend it. Maybe I just define the extension. So if
So I don't get it. The LNs, is it a parameter here somewhere? And where?
yes, it means with respect to the n. So it means that for any I, the set of all n's for which Kn minus Ln is bigger than I is in Dn. Is the limit with respect to this filter, I mean.
Where is the Ln coming from? This is an L? It's an L, right? Where's the L coming from? The
L
LNs.
is the length of Gn. Here.
Oh, I see. So this is a sequence of games. Okay.
Yeah. Okay. So maybe before I define the order on these approximations, I say why I said then approximation. Given S as above, let us define HS to be the set of all functions H1 and H2 such that H1 is in the product of Mn1s, H2 is in the product of Mn2, and this is the main part. You know, I have Fn, recall Fn is a function, and I require that this holds the set of all n less than omega such. Fn is this one, recall the last function which this S takes, yes. Fn of H1 of n is H2 of n. And I recall these be in the filter. So Fn is just the last function related to Gn. And the point of this is the following claim, which is clear indeed. Suppose D containing Dn is an ultrafilter. Or maybe I didn't say, but I always assume all ultrafilters are non-principal. Yes. Clearly, I have to assume it. And let S be an approximation. Then, if we define the function H, which is related to D and which is related to S, just with the isomorphism classes of elements of HS being the equivalent, the pair, the equivalence class of H1 and H2, and H1 and H2 is in HS. Then this defines a partial isomorphism. So this defines a partial isomorphism from the ultraproduct of but this is just partial. And this is clear because, as I said, Fn defines a partial isomorphism. Yes, the player 2 was playing partial isomorphism. So this follows from the way we define the game. And this is clear. So the whole thing is to, and now what I do, I have the assumption Dn is aleph 1. So I will use it to define an increasing sequence of this S. But now I would like to define what is the order. Suppose S and say T are approximations. And then I say S is less or equal APM of T if and only if the set of all n less than omega, such that, you know, S was an omega sequence, yes, G, maybe I denote it by Sn, which is related to S, is an initial segment of GTN. This is the sequence related to, and this is in the n. So this is a large set with respect to the n. And you know, I can do it because of this second assumption. So this is why this is an important assumption, because otherwise maybe we can take some S which has no extensions, but this allows us to find always some extension. And indeed, it is quite, again, easy to prove the following to lemma that APN with this relation is, maybe I call it aleph 1 close if you look at it as a forcing notion, okay? And this means that any increasing sequence, any countable increasing sequence has an upper bound. And the second one is a kind of extension property. And this says that suppose, for example, S is APM, and suppose I have a sequence Wn n less than omega, where I have a sequence Wn, where Wn is a subset of Mn. Maybe it can be 1 or 2, so I write L. But of size atmosphere, okay, L can be 1 or 2. And Wn is an element of M and L to the K. And then I can find some T which extends this S, and such that for each N. Now let's look at LSN. Because it was something less or equal to Kn. If it's Kn, so I can't extend Ts. But if it's less than such that this is less than Kn, then I would like to add this set also as a part of the domain of the last Fn. Recall that each element of S had at stage n, it has some Fn. So here we have two cases. So if L is 1, we reward with Mn1, so we should take it in the domain. So in this case, Wn is a subset of domain of F maybe I call it T. It's related to T. So I will add one point above and will make it. And this is possible by the definition of the game, yes? Because it's clear. And if L is 2, we require the same, but now with range. So the second part is also clear, just by the definition of the game. And now I am ready to prove the theorem and to prove it indeed. Now I use my assumption dm is equal to undefined. So for L1 or 2, take maybe FLI, I less than omega 1, be a family in the product of M and L to the Kn. So each Fn, FLI is here, and it witnesses that dm is undefined, such that for any beta from omega into omega, there exists some I less than omega 1, such that for almost dm many n's, eta n is the FLI. This is just the definition of dm being undefined. Now by induction, choose Si, I less than omega 1 of these approximations. I say it's clear now, yes, such that, I want to cover all elements of the product of Mn1 and also all elements of the product of Mn2. This is clear by part 2 of these lemmas. So I will do some kind of back and forth. So if I is say 2j plus 1, so if it's odd, then choose, maybe I just say less or equal to APN increasing, yes. Choose an increasing sequence. This is possible by first part of the lemma because it's only one close. Then I require that for all n less than omega, if L SIN is less than Kn, then I require that F1 excuse me, this is 2j. So suppose I have defined S2j, L S2j at point n. Then I require that Fj at n is a subset of domain of Fsi at n. And this is again the function related to Si at level. And if I is even, I require the same. But now for range. 2j plus 1, if this is less than k, and then Fj1 of n is a subset of a range of Fsi. So I can't do it by the previous lemma, yes. And now the point is that if we let H just be the union of H, T, Si, I less than. So I fixed D, these are ultrafilter containing Dm. These indeed, not that since SIs are increasing, these HD SIs are also increasing. This is increasing. But the point is that the domain is exactly this, the whole ultraproduct. And this is because of this cover property. And the range is the whole Mn2. So indeed, H defines an isomorphism. And first part 1 follows. Any questions? Now I turn to the proof of 2, and this is quite easy. So we want a model in which dm is aleph 1 for each m. And for this, so, excuse me. I will use it's an iteration of length omega 1 of final support iteration where at successor steps I force MA. And to show that it gets the result, just maybe I just mentioned this lemma first. Suppose MA kappa volts, yeah? And let A be a subset of omega to the omega, be of size less than kappa. Then there exists some F. Oh, okay, maybe just fix M. This is an ultraproduct. Yeah. There exists some F in the product of omega to the Kn and less than omega, such that for any eta in A, and there are the m many points n such that eta in is in F. And the proof of this is maybe, I assume it is well known. We don't know. And anyway, maybe I just sketch the proof. Maybe at least I introduce the forcing. A condition is a pair. So P is Kp. And I want to define an approximation to this function F. So it's, so maybe I call it F P, where Kp is finite, Fp of n is in omega to the Kn, or maybe I just say less or equal to K. And the main thing to allow me to extend, to be able to extend condition is that the set of size of these FPNs and less than omega is bounded. So it's not quite, it's not getting quite large. And the extension is different in the natural way. So I say Q extends P if, okay, K of Q should be at least K of P. And I assume that for all n less or Kp, Fq of n and Fp of n are equal, and for all n, Fq of n includes Fp of n. So on the natural. This forcing is CCC, and I can easily show that it satisfies the requirement, because for any eta I can define a dense set, and so it's quite easy to verify it. So I can maybe just skip it. And now let lambda I less than omega 1 be an increasing sequence of regular coordinates. Okay, since I just want to prove consistency, I assume GCH in the ground. Okay. Define a finite support iteration. Maybe Pi I less than equal to omega 1 and Qi I less than omega 1. Define finite support iteration such that for each I, maybe I can assume this is increasing and continuous. Oh, it's not really needed. But maybe just to state this the first. For each IPI has size lambda I and PI star QI. So this is just PI plus 1. Forces 2 to the aleph 0 is lambda I plus 1 and N. So I can do it, yes? Yes. And now P omega 1 is as required. Just by the previous, just by this lemma, because given any M, it belongs to some initial segment, and at each step, I just, at a step, say I plus 1, I dominate all functions which are generated by PI, by one element, by just one function using PI plus. So I build an omega 1 sequence of functions, and it witnesses the dominating number for M is aleph 1. This finishes with the proof. And maybe I just finish my talk with stating more results, but not proving that, but not proving them. As we saw in this proof, the continuum was singular of cofinality aleph. But indeed, we can prove, we can make postulate regular. And this is the theorem that I mentioned. The following is consistent. Okay, maybe just first fix this. Suppose lambda is a regular cardinal bigger than aleph 1. Then in some forcing extension, in the 2 to the aleph 0 is lambda, and this is also the bounding number. And 2 for any ultrapolar problem M, and any ultrafilter B extending the M if the ultraproducts are elementary equivalent, then they are result. So okay, I don't want to talk about the proof, and I would like just, we have proved this, but now I would like to state one more theorem which is in progress. So maybe I write theorem star work in progress. And in this theorem, we relate our work to the Axe-Quotient theorem. Maybe before I state the theorem, I just recall a few results about the Axe-Quotient. We have two kinds of Axe-Quotient theorems, maybe at least, maybe I would like to say two ones. The first one is Axe-Quotient Kirchhoff principle. It says that for any non-principal ultrafilter B on primes, for any non-principal ultrafilter B on the prime numbers, the ultraproduct of QPs mod B and FP of T's mod B are elementary equivalent. Q of P is the field of p-adic numbers, FP is the finite field with P elements, and FP of T is the Lorentz series over FP. And of course, this is indeed isomorph, more equivalent to saying that the product of ZP mod D. They are equivalent. And now the point is that if we assume CH, then this elementary equivalent becomes isomorphism. Then for any D as above, in these ultra products are isomorphic. And this just follows from model theoretic fact that both of these structures are saturated, Aleph1 saturated of size Aleph1, and since they are elementary equivalent, they are isomorphic. And very surprising, maybe just as an exercise, if we assume this, we can prove this statement. It's not that this is a ZFC result, but this is not. But it is not difficult to show that if we assume this stronger assumption, which also, of course, assumes CH, then we can prove this ZFC result. And the idea of the proof is this. Okay, just take a non-principal ultrafilter B, force with coin forcing to add a new subset of Aleph1. It forces CH and doesn't add any new reals. So in the extension, we know that these ultraproducts, so D remains an ultrafilter in the extension. And in the extension, the ultraproducts are isomorphic. In particular, they are elementary equivalent. But this can be expressed by can be quoted by a subset of omega, yes, because we're just talking about formulas, sentences. So by absoluteness, I can go back to the V and conclude that they are also elementary equivalent. And now the work in progress is to show that the converse of this theorem does not hold. So it is consistent that CH fails, and for any, or maybe for any non-principal ultrafilter D on omega. Well, maybe I say again, related to this QP and FP, we need to define a filter and for ultrafilters extending that filter. The ultraproducts of QP, mod B and FPT mod B are isomorphic. Note that the previous results don't show it because QP and FP of T have size continuum. So if CH fails, they are larger than Aleph1, and our arguments don't work. So there's not much more work to be proved, but it's not yet complete. So maybe just okay. Okay, I'm finished, and thank you for listening. And if you have any questions,
Thank you for the talk. So
Yeah,
yes, questions, please. So I have a question,
okay.
very naively. So, I mean, it's conceivable that there are model sequences where, you know, this sort of this, I mean, little m's with double underline, where this principle that elementariness implies isomorphism
Excuse me,
also implies CH.
which one?
Well, I mean, if you know, if in 2 here you put some other models, could it be that theorem star is wrong? I mean, what if you wanted to prove this for a particular model sequence different from the one here with QP and
Different
FP?
for? Excuse me, I don't hear quite well, and may you repeat it?
If you take a different sequence of models than QP and FP,
Okay.
of course, which are elementarily equivalent. That's so that the product is elementarily equivalent.
Mhm.
And you ask 2 in your theorem star that they're isomorphic.
Okay. Yes. Yes.
Is it possible that you recover CH if you take, I mean, is there a sequence of models where the isomorphism will
Gives us CH.
give? Yes, exactly.
So, but we are proving the consistency of not CH plus star for all n.
What
It's
is
not just-
star? I see. Oh, okay. So this is not.
Oh,
Okay.
it's not just for
It's not
fixed n.
possible.
It's
Yes.
for all
Yes.
n.
So that's what you showed. I see. Okay.
Yes.
Right. Okay.
Okay, here, yes. It's for all n, not just for some fixed n. It's for all n.
Yeah. I see. Oh, yeah. Okay. That was a silly question. Right. Well, I mean, okay, but it's what if, so the question is what, so yeah, okay. So that was actually something I also wanted to ask. So what, I don't really have an intuition as to what this game actually means, what it means, what condition 3 means in the definition of ultra power problem.
In the game, yes.
Yeah, I mean, can you give some sort of indication as to?
But you know, it's a kind of errand for us. It's a variation of it. So if
Yeah, that's clear. I mean, but I mean, how restrictive is this for such a sequence of models?
Usually, no, you know, MNs are models of tau, and tau is the union of tau n's. So, and for Aaron for us again, just because, you know, if here we talk about tau, it's infinite, okay? So it might be infinite, an infinite vocabulary. So maybe just take this F0 might be finite, its domain, I mean, or its range. But if the tau is infinite vocabulary, maybe we can't touch anything. So we just cover tau as an increasing sequence of tau n's, and we talk just about partial information. But when we go up, we are enlarging these tau n's. And since we are talking about ultraproducts, okay, so at the end, just, you know, if finite informations are not really important.
Let's put it this way. Can you give me an example where this fails? An example of...
I think this, for this QP and FPT, they satisfied by X question, Kirchhoff principle. Indeed, for all large enough n, they are elementary equivalent.
Yeah, because otherwise, of course, this couldn't be. Yeah, you couldn't go about proving theorem star if it satisfied this. But I mean, okay. A simpler example? You don't have a simpler example?
Maybe just talk about dense linear orbits.
Okay.
Yeah, very simple. Just about any two. Just think about each mn1 and mn2 is a model of is a dense linear order. So of course, in that case, each kn is just n. Yes. Yes, each kn is just n. So you can conclude. Yeah.
Yeah.
Okay.
So interesting. Okay.
So in your consistency result,
Yes.
that David was asking about, you say, of course, you have it for all these model problems. But I think the question was, could you have the consistency for certain class of model problems having the invariant be aleph 1 and for other models not? For example, take the theory of, let's say, graphs and hypergraphs of different sizes. Could you have the cardinal invariant for, I don't know, graphs being aleph 1 and for triples not being aleph 1?
But as I said, just I can say that the models n1 and n2 be of size atmos aleph 1. So they can be also of size aleph 1, not just contained. But I don't know that your question.
Can we see again the definition of this DM?
The definition of DM?
Yeah, the cardinal invariant. I forget what it's called.
Here. It's the cardinal.
Right. So I mean, so in your in the paper that that I looked at, you're proving something under the hypothesis that covering of meager is the continuum, right?
Yes, that's the completely different proof. It's not.
So that's a completely, because I was wondering,
Yes,
because here you're assuming DM is aleph 1, so it has a completely different flavor.
Yes, completely different proof. I didn't talk about it. The proof is completely different. In that proof, we build the ultra filtering on 2 to the aleph 0 many steps, and we use this covering to be able to continue. You know, the point is that the covering of meager being 2 to the aleph 0 is elementary, is equivalent to MA for co-enforcing.
Yeah.
MA for copulation 2 to the aleph 0. And we use this. So, and maybe I just say in the theorem that I talk also about bounding number. And there, this dominating for each n is also 2 to the left in that model. So the proof is not the same as this one. It's different.
Interesting.
Yeah, it's
so
different.
So I mean, I'm not sure if this is worthwhile, but if you wanted, of course, you could extract a forcing from the forcing that you have that sort of adds the isomorphism, right?
Forcing.
Isn't that, I mean, is that, can you view it as?
No, here, the idea is, here, you look at the previous proof. We had the sequence of SIs of length omega-1, yes? But we
Yes.
can't continue it. But in this proof, we define a stronger relation between approximation points, S. It's just less or equal star, okay? And then we build an increasing sequence of lengths continuum, and such that exactly the same, they cover all WNs. In the proof we had, maybe I come to the lemma here, part 2. Here we build an increasing sequence of lengths continuum, which is less or equal star. And we make sure this holds for all sequences during the iteration. It's just a bookkeeping argument. So it's not really difficult.
It's not really what?
Difficult.
Uh-huh. Mhm. Okay. Are there any other questions?
So thank you for the invitation.
Yes, and thank you for the talk.
Yeah, thanks for the talk.
Thank you.
Okay, then I will conclude the session. Goodbye, everyone, and thank you for attending.
Bye.
Bye. Thanks again.